Welcome to Chapter 6. We're going to be talking about heat, temperature, thermodynamics, and we're going to start off with just a little bit of information about energy, which is actually from Chapter 5. So we need to talk about energy in order to be able to understand what is going on with heat, temperature, and thermodynamics. So let's start off with energy. So what is energy? Energy is just the ability to do work, to be able to apply a force over a distance. So you're familiar with this just by doing work, for example, for picking up a box or pushing a cart, anything that is involving moving objects any sort of distance. So the thing is that we only see the effects of energy when it is either being transferred from one place to another, so when it's being moved from one object to another, or if it's being transformed from one form to another. And so what do I mean by that? Because as far as transferring it, that makes sense, right? You have your energy and you push on a cart, that energy goes into the cart to make it move. But as far as transformed from one form to another, here what we're talking about is, for example, if you have electrical energy and you use that electrical energy to heat something. And so heat energy, thermal energy, is another form of energy. So you took electricity and turned it into heat. And so that's the transformation. We can't actually see the energy, but what we can do is see its effects. And so that's just a little intro into just generally what energy is. We need to talk about the two different types of energy, though, to understand heat. So potential energy. Potential energy is officially defined as stored energy due to position, shape, or state. So what are we talking about? So potential energy, very often people talk about potential energy as, for example, a ball sitting at the top of a hill, or a bike, a bicyclist who has pedaled to the top of the hill and is sitting right at the top of the hill. That would be position. Or for example, if you pick up an object, like I've got this little paperweight on my desk, when you pick it up and you hold it, right now, this paperweight has potential energy due to its position because I've picked it up and it's got more energy now. It's stored energy due to where it's located. Shape. So examples of shape would be things like stretching. So if you stretch a spring or a rubber band, things like that. State generally is talking about things like is it in a gas state and so forth. The thing is potential energy is stored energy, meaning that it's not currently doing any work, but it has the potential to do work. And so I do have some examples written down here. So a drawn bow, that would be an example of shape. So like a bow, from a bow and arrow, when you pull that bow back, you are storing energy that you can transfer to the arrow when you release the bow. The stretch rubber band, that would be another shape example. When you stretch the rubber band, I'm sure you've all played that game before with somebody. It hurts when you let it go and it flicks somebody. That's because that stored energy is being transferred. And then compressed spring. And then one that we don't think about, but it has a lot of potential energy, is food. Because another place that potential energy can be in, and this is actually related to state as well, is in chemical bonds. So energy can be stored in chemical bonds. And then by breaking those bonds or putting those bonds together in new configurations, you can get energy out of them. But as long as they're just sitting there by themselves, not having anything done to them to have released that energy, they're still potential energy. So what I'd like you to do is take a look at these three balls. So we've got a ball that was lifted straight up, a ball that was rolled up an incline, and then a ball that was rolled up this set of stairs. The height of all of these locations is 3 meters. So the question is, which ball has the greater potential energy? So I would recommend that you pause the video at this point and think about it. This is, the sort of question that can show up on, exams and so forth. So think about what's going on here. And the answer to this question is all 3 of these balls have the same amount of potential energy. It doesn't matter how the ball got there, because all of the balls are at the same height, they have the same amount of stored energy. So yes, these 2 balls over here had to travel more of a distance to get there, but they're at the same height and they have the same amount of potential energy. This is because, in this case, they all have what we call gravitational potential energy. So gravitational potential energy does have an equation tied to it. Yes, this is a science class, so there is a little bit of math in it. Not a lot, but a little bit. So to calculate gravitational potential energy, it's pretty easy. So you need the weight times the height. But very often we don't actually have the weight, we have the mass of an object. And so that's why you've got this other equation down here. So gravitational potential energy is equal to the mass of the object. So that would be given in grams or kilograms for metric. And then you're going to multiply it by gravity. Now, gravity is a constant, and I'll remind you of this at the beginning of any exams or so forth that you're going to have, that you would need it. But the constant for gravity is 9.8 meters per second. So that's always going to be what gravity is. Okay. So you got the mass of the object, so in grams or kilograms. You've got gravity at 9.8 meters per second, and then the height will generally be given in meters. So you can calculate how much potential energy an object has based on these 3 measurements. Oh, I got to turn my pen off. So examples of gravitational potential energy, things like reservoirs. So this is why we put dams on rivers, is so that we can build up the water behind them and then let the water out of a very small area. And then we put a turbine in there, something that can turn so that we can capture that energy as the water flows through. Bikes at tops of hills, sleds at tops of hills, so sledding downhill, that's how you get to your energy and get to go faster, and then the balls that were on the previous slide. So here I've got some practice problems. So in this video, I'm just going to show you the practice problems. I will post another video where I will walk you through the solutions on these 2 problems. So if you want to try them yourself, you can go ahead and try them. These are examples of problems that can show up again in future exams and so forth. So you want to give these a try. So these are looking for potential energy. The first one is looking for the potential energy. The second one is using that same formula, just using it a little differently. In this case, looking for the height of the shelf. So again, if you want to walk through the solutions for these, I'll do those in another video that you will be able to find in this section of the lessons. So if it's not potential energy that we're looking at in an object, then we're looking at the kinetic energy. And kinetic energy is the ability of an object to do work on other objects because of the motion. So this is basically the energy of motion. So Think about objects that would collide into each other. They're going to be able to push each other and transfer their energy. Think about like a bowling ball. Bowling balls, you're going to make the bowling ball roll. It's going to hit the pins and the pins move. And that is kinetic energy, that motion of rolling of the ball. That's kinetic energy. And then it's going to transfer that energy, some of it, to the pins to make them then have kinetic energy. So there is an equation as well for calculating kinetic energy. Kinetic energy is equal to 1/2, so you multiply this rest of the equation by this. The mass of the object times the speed of that object squared. So the easiest way to do this is to take the speed and multiply it by itself. That'll get you the square. And then multiply that by the mass, and then multiply that by 1/2. And again, I've got some practice problems on the next slide, and I will walk you through the solutions on those. But let's just real quick, we can do one here. So let's say that the speed of this object is 2 meters per second, and the mass is 10 kilograms. Okay, so you take 2 and you multiply it by itself, so you square it. So that would give you 4, and then you'd multiply that by 10, and then you'd multiply that by the 1/2. So multiply 1/2 by 40, which would get you a kinetic energy of 20. All right. So let's see. There we go. This is the other way you sometimes see it written. Kinetic energy is equal to 1/2 times mass times velocity squared. It's the same equation. Velocity for what we're looking at is the same as speed. Just so in case you see that, that's why I put both of those in there. So what does that mean? Well, what that means is because of this square over here in the equation, small changes in the speed of an object create very large changes in the kinetic energy. And you may actually be pretty familiar with this. If you think about it, the faster an object is, the more it hurts when it hits you. So if you're just tossing a ball back and forth pretty slowly, if it hits you, it's not going to hurt very much. But if somebody picks up that ball and wings it at you, it's going to hurt a lot more. And that's because that ball has more kinetic energy because it was going faster. This is also why, for example, if you're in a car, it takes longer to slow a car down when you're going at higher speeds, because it has more kinetic energy the faster it goes. And so if you're only going 20 miles an hour, it's going to take a very short distance to stop your car versus if you're going 40 miles an hour. It's not just double the amount of time to slow your car down. It's more than that because of this increase in kinetic energy on your car. So, like I said, I've got some practice problems here. So going back, I mentioned bowling balls earlier. So these are problems using bowling balls with the kinetic energy equation. And so it's 3 different problems using those bowling balls at different masses and at different speeds. And so again, I will post a separate video on the solutions for these. So if you want to try them on your own, then you can watch those solutions and see if you figured out how to do them. This is the end of the energy section, and The next section will start talking about the material from chapter 6 on heat and temperature.